Hello everyone. In the previous session, we have discussed about G delta and F sigma sets, and here we have a theorem based on that concept. Please go through the previous video, and this is important question which is asked in the year 2018. So here is a statement: if E is any set in R and E is subset of R with measure of E is less than infinity, meaning is measure of E is less than infinity in the sense it is finite, that is it should be less than infinity, then there is an open set O which contains E, or else I can read this as E is contained in O. So O is a larger set in which E is there. Fine. Then such that we have to prove that measure of O is less than measure of E plus epsilon. And second statement, if there is G delta set and E is contained in G, in the sense G is a set which contains E, if G is a set which contains E, or else I can write G here itself. G is contained in E. Then we have to prove measure of G is exactly equal to measure of E. This is important question. Now let me prove the statement 1. Proof is very simple. Just the logic is, first let me write down the given statement. Given that E is subset of R and moreover measure of E is less than infinity, in the sense it is finite set, or else I can say it is a countable set. Then as per the definition, there exists a countable family of intervals, say En, such that n is equal to 1 to infinity. E is subset of union n is equal to 1 to infinity In. Hope so you remember this. It is by the first property of outer measure, or else I have told you this in proving theorem 1 itself. That is, if A is any open set, I can write A is subset of union n is equal to 1 to infinity In. This is I have proved clearly if A is open. Since E is also an open set, why? Because it is contained in an open set O. So E, I can write E as subset of union n is equal to 1 to infinity In. This is by theorem 1 that I have already proved. Fine. Here no need to write. So why? Because I have already proved that by theorem 1. So that is why I have written this statement. And while proving the translation invariant property of outer measure, I have given this statement that summation length of an interval is less than measure of any open set plus epsilon. We have already proved this. You just go to the theorem of previous session where I have proved the translation invariant property. So as per the property, there exists an epsilon greater than 0 such that length of In is less than measure of E plus epsilon. I have already proved this in outer measure, properties of outer measure. You just go through the notes that I have already given. Fine. So by that property I can write like this. See, I have forwarded these notes to you only. I am just showing you just for your reference. See here, by translation invariant property I have written this statement. So A is open set here. So same property I have used here, but I have considered E as an open set. So instead of A in the property, I replaced it with E. Clear? Now, so I can write this property. Let me take this as equation 1. Since E is a subset of O. Clear? Why? Because E is a set which is in open set O. I have a set O. E is contained in it. So if E is subset of this all the open intervals, I can say O is equal to n is equal to 1 to infinity all the intervals. Clear? Why? Because it is already given that E is contained in O. Now let me take measure on both sides. So you will get, it is not 0, O it is. Measure of O is equal to measure of union n is equal to 1 to infinity In. Now as per the theorem, what we proved is, suppose if you have measure, if you are going to take this inside, this union will become summation and this equal symbol will become less than or equal to. You have already proved this in one of the theorem that m star of A is equal to, I'll just write the theorem here, m star of A is equal to m star of, less than or equal to, suppose if you have union, let me take this inside, it will become summation n is equal to 1 to infinity m star of An. You have already proved this. So let me use the theorem. So I am going to take measure inside. You will get summation n is equal to 1 to infinity. So the minute when I take measure, it is none other than length of an In. Or else if you want, you can write one more step. M star In. or else I can write this as n is equal to 1 to infinity length of in, m star of 0. Clear? So m star of 0 is less than or equal to length of in. What we have assumed by equation 1, I can replace this with the given expression, right? That is m star of o is less than or equal to m star of e plus epsilon by equation 1. So this is what the proof of the first. And remember, here you are not going to get less than or equal to. Clearly it is less than. Why? Because this expression is less than, clearly less than, it is not equal to. So that is the reason less than or equal to will become less than here. You should not put equals here. Remember, this follows the proof of first. I am repeating once again, since it is clearly given E is one of the set in a given set O. O is an open set, E is contained in O. Fine. Now let me, if that was the case, I have already proved in theorem 1, A is an open set, then it can be expressed as union of all the open intervals. So I have written the same, and I used the property of translation invariant. I have written the statement as it is. Where I have set A, I have replaced it with E. Fine. So if E is the subset of all the intervals, E is contained in O. Meaning is O is the largest set compared to E. So I can replace E by O. That will be exactly equal to all the open intervals. Now let me apply measure on both sides. I have used the theorem here. The minute when you apply measure, union will become summation and equal will become less than or equal to. So measure is none other than length of an interval. So I have replaced measure with length. Since length of an interval is always less than, it is not less than or equal to, it is always less than. So I replaced equation 1 in this, so that I have obtained measure of any open interval is less than measure of E plus epsilon. This is the proof of first one. Now get into the proof of second one. Now proof of second one is that, suppose if G delta is a set and E is contained in G, look at the diagram, E is a set which is contained in G. G is this largest set, again G will be in O. Now I can clearly write that for each n, or else let me write directly, for each open set E, O is an open set and E is contained in O. Clearly I can write measure of O. I am applying just measure to this. Measure of O. So when I apply measure, this subset will become greater than or equal to measure of E. Right? Why? Because suppose if you have E is contained in O, when you apply measure, this symbol will become less than or equal to, right? Or else I can write either it may be equal to O or it may not be equal to O. So that is the reason I can write less than or equal to. Fine. So I have applied measure on both sides. Now I'll just manipulate this equation in such a way that measure of O is greater than or equal to measure of E, which is less than measure of G. Shall I write like this? Why? Because see here, G is a set which contains E. So when you apply measure, measure of this set will be larger than measure of E. Why? Because E is contained in G. G is the largest set in which E is there. So measure of this G set is larger than measure of E. Or else I can say measure of E is less than measure of G. So that is why I have written like this. Now I can rewrite the expression. I'll remove this expression, or else I will omit this expression. I can write this: m star of E is less than or equal to m star of G. In other words, I can rewrite this as m star of G is greater than or equal to m star of E. Clear? Let me take this as equation 1. What I have obtained is m star of G is greater than or equal to m star of E. Let me take this as equation 1. I am repeating this once again. It is given in the problem itself. I have applied the measure. So the minute when you apply measure, no matter whether it is subset or proper subset, you can replace it with greater than or equal to. And I have applied measure. Clearly E is contained in G. In the sense G has greater measure compared to E, or else E is lesser measure compared to G. So that is why I have written like this. Now I'll leave this first expression. Let me consider next two expression, so that I have arranged that so as to get equation 1. Fine. Now let me take G as an intersection of all the open intervals. Intersection of all the open intervals O. As per the definition of G is intersection of all the open intervals. So that is why I have written like this. Now let me apply what we say measure on both sides. So m star of G is less than or equal to measure of On. I can write. On is all this, what we say, open intervals. So when you have equals also, whether it is union or intersection, I can write like this, right? Why? Because see here, O is one of the open interval and G is a set inside and E is inside the G. I have written here, see here. So clearly measure of this O or else this G, this one is G. Let me rewrite once again. Open set O I have, and within O I have G. So measure of this G is always less than measure of O. I have considered G as intersection of all the open intervals. This is by definition of G's delta set. Now this expression I have assumed. Why? Because G is subset of O, or else I can say G is contained in O. O is the largest set and G is inside O. So I can write measure of G is less than or equal to measure of On. Now I can write the same as m star of G is less than or equal to, just now I have proved here, On is for n number of open intervals. Just now I have proved that m star of O is less than or equal to, less than measure of E plus epsilon. So I can make use this property here. So when you use that, you have to write less than. There will be no question of equal to. Why? Because we have an expression only less than m star of E plus epsilon. Clear? Since epsilon is very small, we can eliminate that or we can neglect it. Then I can write m star of G is less than m star of E. Now one with less than symbol, let me take this as equation 2. One with greater than, no matter whether it is equal or not. One is greater than and another is less than. So from 1 and 2 I can say m star of G is less than or equal to m star of E. I have combined equation 1 and 2 so as to write equal sign. I am repeating once again. The proof of second one is, before going to proof of second one, you just revise, you just go through this diagram. O is the largest set in which G is there. Inside G I have a set E. Clear? Now since O is subset of E, or else I can say E is subset of O, or else I can say E is contained in O, or else I can say E is subset of O, one and the same. So let me apply measure on both sides. As per the property I have written this, and now E is a set which is contained in G. E is subset of G. So that is how measure of G will be greater than measure of E. Is equivalent of saying measure of this E is less than measure of G. This is the smaller set, this is larger set. So measure will be larger for G. So that is why I have written like this. Now leaving this first expression, I have considered these two expressions and I have manipulated in such a way that I have obtained equation 1. As per the definition of G delta set, G is an intersection of all the open sets. Now since G is a set which is inside O, so I can write measure of G is less than measure of O. Why? Because O is the largest set and G is inside O. So I have written this statement here. Now what I did is measure of O I have already proved by expression 1, it is less than measure of E plus epsilon. No matter whether it is less or equal, here I have equal sign. Either you can carry that or else you can keep less than as it is. So let me call this as equation 2. Equation 1 and 2 follows that they are equal. So hence the proof of the second statement, measure of G is equal to measure of E. So I have proved measure of G is equal to measure of E. Hope so it is clear. It is important concept and it is asked in the year 2018, second B sub question it is. And measurable set is none other than, before going to the measurable set, let me revise the concept of set theory. As you already familiar, suppose if I have any set A, say subset of R, where R is a real number, I have considered one of the set such that A is subset of R. And if E is any set, then we can write A as A intersection E union A intersection E complement. You have to remember this property. It is already there in your lower classes. Anyhow, I'll give you only one counter example. Suppose if I have a set A, say with an element 1, 2, 3, 4, 5. Fine. And let me say a set E. So this is clearly subset of R. So I have considered a set A. I have considered one more set E, say with an element 3 and 4. Now clearly it's complement. E complement, how you're going to calculate? It is set of all the elements which are not in A. That is E complement formula is A minus E. So after subtraction, you will get E complement as remove 3, 4 elements. So you will get 1, 2, 5. So E complement is A minus E. Now let me find A intersection E. A intersection E is 3, 4 common elements, right? Similarly, A intersection E complement. A intersection E complement is 1, 2, 5. Fine. Now let me combine these two. That is union A intersection E, union A intersection E complement. So when you apply union for these two sets, you will get 1, 2, 3, 4, 5. Right? Clearly this set is equal to the given set A. That is what I have assumed. That is, for any set A, intersection E union A intersection E complement is equal to A. I have given a just counter example in order to remember this. You have to remember this property. Fine. So suppose if I have this inequality, or equation, A intersection E complement. Remember, if you are going to apply measure for this, M store of A will be always less than or equal to. Sometimes it may be exactly equal, sometimes it may not be equal when you are going to take measure. So, meaning is that suppose if A has some elements, say 4 number of elements, it may be equal to 4 elements or it may not be equal to 4. Obviously it will be less in some certain cases. So when I apply measure for this inequality, I'll get M store of A is equal to M store of A intersection E union will become plus. Remember, union will become plus M store of A intersection E complement. You have to remember this property. For any set A, measure of A is always less than or equal to measure of A intersection E plus measure of A intersection E complement. It is obvious and it holds for all the sets. Or else I can write it holds always. You have to remember this. Now coming to the property of measurable set. Concept of measurable set. Measurable set in the sense, suppose if I have a set A which is a subset of R, in the sense real number, or else I can say A is one of the set which is in a real number. If A is said to be measurable, A is said to be measurable in the sense the set is said to be measurable if for any measurable of this A will be exactly equal to M store A intersection E plus M store A intersection E complement. I am repeating once again. Any set A which is subset of R is said to be measurable only when M store of A is equal to M store of A intersection E plus M store of A intersection E complement. E is also one of the set in R. Fine. So if this inequality holds good, then clearly I can say A is measurable set. A is measurable set. Clear? Remember, if they asked you to prove, or else when do we say a given set E is measurable? Only when if this inequality holds. Fine. And I have already told you this inequality holds always, no matter whatever may be the set. So it is only sufficient to prove that M store of A is greater than or equal to this expression. Why? Because it is obvious. This result is universal result. It holds good for all the sets. So M store of A is less than or equal to this set. Now when do we say a set is measurable? Only when it is equal. So less than or equal to is obvious. So we have to prove is greater than or equal to. Then by these two we can combining, we get measure of A is equal to measure of A intersection E plus M store of A intersection E complement. Then we can say the set E is measurable set. Overall definition is that suppose if I have two sets, say E and A, which are in a set of real number. Fine. Then this set E is said to be measurable. E is said to be measurable only when this condition satisfies. That is M store of A is equal to M store of A intersection E plus M store of A intersection E complement. Clear? Now let me talk about few properties of measurable set, or else I can say examples of measurable set. Remember, or a set of real number is measurable. These are key points. It will be helpful for KSET exam. Fine. And remember, null set is also measurable. Example for measurable set. And third one, what we say, complement of measurable set is also measurable. Or else I'll give the proof of that particular statement. Counter set, Cantor's ternary set. You're already familiar with this concept as I explained in his previous class. So Cantor ternary set is also measurable. Remember these three examples: set of real numbers and a null set and a Cantor set is always measurable. And fourth one is that a set of measure 0. Set of measure 0 is measurable. Meaning is that if I have a collection of sets which has measure 0, then those sets is measurable. I'll give you proof of this. Suppose let me take E is a set in R. Then measure of E will be 0. What I'm trying to say is set of measure is 0. In the sense E is a set whose measure is equal to 0. Now we have to prove this is measurable. So when do we say measurable? If the property holds good. Just now I have told you by the definition M star, if this property satisfies, then we say the particular set is measurable. Now let me verify the property. Fine. So what I have assumed is E is a set which is having measure 0, and clearly I can write A intersection E is always subset of E. See, for each and every concepts I cannot give counter example, but anyhow that is understood. This all inequalities comes from set theory, which is basics. But anyhow I'll give one simple example. Wherever is necessary I'll give counter example. Rest of the inequalities you have to understood. If you're not understanding particular concept, you go through taking what we say counter example, then you will clearly understand. Suppose let me take A with an element 1, 2, 3, 4 and E with an element 2, 3. Fine. If you're going to take A intersection with E, intersection is none other than common elements. Fine. So A intersection E is 2, 3, which is clearly subset of E, right? Why? Because it contains the elements which is in E. Suppose let me take one more example like 5, 6, 7, 2 and E with an element 2, 3. Fine. Now if you're going to take A intersection E, element will be 2. Clearly A intersection E is subset of E, right? See, 2 is in the set E. I can say A intersection E is subset of E. So that is why I have written this. This is a standard expression. If you are going to take intersection with any of the element, you will get the same element only. So A intersection E is subset of E. Now what I'm going to do is let me apply measure on both sides. So M store of E is less than or equal to, when you apply measure as per the property, it will become less than or equal to M store of E. I can write. Now I have already proved what I have assumed is measure of a set which is equal to 0. So M store of E is 0. So I can replace this as M store of A intersection E as 0. Now I have already told you by the properties of outer measure or Lebesgue outer measure of a set that for any non-measure, any outer measure of a set is positive, right? Outer measure of a set is positive. You just remember this statement. Now as I have written this inequality, similarly I can write A intersection is complement will be subset of A. I will take this counter example in order to convey this particular statement. Suppose if I have A with set 5, 6, 7, 2. Fine. And E is I have taken as 2, 3. Let me write once again 2, 3. Now let me calculate E complement. E complement will be A minus E. Fine. So A minus E will be, just I have to remove 2, left with 5, 6, 7. So this is what E complement is. Now let me calculate A intersection E complement. So do we have, this is what E complement is. A is this one. So common element is 5, 6, 7. Clearly A intersection E complement is subset of A. Why? Because an element 5, 6, 7 is in the set A, but they are not in set E. Clear? So that is why this expression holds good always. So when you are taking intersection with complement, first set you are going to write. When you are going to take intersection with a given set, second set you are going to get. These are standard inequality you have to remember. Anyhow, I have given a counter example for the particular statement. Now I can write A intersection E complement is subset of A. Now what I am going to do is let me take measure on both sides. So M store of A intersection E complement is, when you're going to take measure, the subset will become less than or equal to M store of A. Clear? Now I'll just reverse the inequality. Something like if 2 is less than 1, or 2 is less than 3, I can write 3 is greater than 2, one and the same. So in the same manner, I'm just reversing this. So I'll get M store of A intersection E complement. Fine. Now let me once again, I'm going to write the same statement is greater than or equal to M star of A intersection E complement. Now what is the value of M star A intersection E is 0. So anyhow I can add 0 here, so that it doesn't make any difference to the given expression. So I can write M star of A is greater than or equal to M star of A intersection E complement plus 0 I can replace with M star of A intersection E. Fine. So at the beginning itself I have told you, when we have to prove a given set is measurable, it is sufficient to prove greater than inequality. We just revise the definition here. Less than or equal to inequality holds always. It is standard for all. Just I have given a counter example. You can go through this. Now we have to prove only greater than or equal to inequality. That is what I have proved here. See here, greater than or equality holds good. Now obvious is less than. It holds good for all the inequalities. It is universal relation. M star of A intersection E. So by these two I can say M star of A is greater than or equal to M star of A intersection equal to, right? Since I have greater than or equal to and less than or equal to, by combining these two I can write equal to M star of A intersection E. Meaning is that the given set E is measurable. Measurable meaning is the inequality holds good, in the sense set of measure 0 is measurable. I have taken a set E which is having measure 0. I have to prove this is measurable. In order to prove measurable, we have to prove this inequality is true. What I did is I have assumed the inequality which is obvious, as I gave one of the counter example to prove the same, and I took measure on both sides. So M star of E is already 0, so I have substituted here. Now I have taken complement of inequality, so I have applied the measure on both sides. By combining the inequality, I have obtained greater than or equal to. Now it is obvious for less than or equal to. By these two equation I can write equals. So any set with measure 0 is measurable. These are the properties of a measurable set, and you have to remember this. So these are 4 properties of measurable set, and fifth one is that if you are going to, suppose if I have a set A which is measurable. Fine. If you are going to calculate its complement, then A complement is also measurable set. Fine. Just I am revising the measurable properties of measurable sets, or else examples of measurable set. Remember, a set of real number is measurable, null set is measurable, Cantor ternary set. This concept is clearly explained in the previous video. Please go through that. And set of measure 0 is also measurable. That proof we have. Why? Because it is asked in one of the years, so that's why I have proved the theorem here. Now it is not exactly theorem, but it is one of the property. You have to know this. And fifth one, if you have any set which is measurable, and if you're going to take complement of the same set, the complement of the set is also measurable, or else I can say a complement of measurable set is measurable. So remember all the 5 properties, and the theorem based on measurability will be continued in the next session. Thank you.